Saxon Algebra 2, Lesson 1. We're done with the lettered lessons. Hallelujah. I won't miss those. We are moving, my students, into the numbered lessons. And you'll see that here on your checklist. We're done with those. So now we're moving into just familiar territory. You watch the video, you do the practice, and you do the odds. Always the odds. We're not going to do the evens unless I specifically say so. So we're now in normal mode, and off we go. There's a lot of review in lesson 1. It's not very exciting. It's all geometry. Well, yeah, it's all geometry. So here we go. Polygons are objects with straight sides. They are closed, and they have no crossing lines. And just for fun, I'll show you in the book some freak children that don't qualify. Here's one that has a rounded line, so no. Here's one that's open. It's not closed, right? It's open. It has an open area. No. And these two both cross over on themselves. Okay? So these are all fails. These guys are all polygons. This one looks weird. It has a cave, which John has helpfully labeled for us. That just cracks me up. It's okay if it has a cave. That's just fine. The rule is down here, it says that if you put dots inside of the polygon and draw a cross from any one of those points to another, it's okay to draw across the cave, but you have to be able to connect it to the other dots inside of it. All right. These are called convex, and this is called concave. I don't know that you're ever going to need to know that, but good to know, right? All right, what we like to talk about are what we call regular polygons. Regular means that the angles within the polygon are all the same size, and the lengths of the sides of the polygon are all the same. This is happy news. What that means is that we like to deal with the objects that are the most uniform and the same. Here are some pictures. Here's a regular polygon with 5 sides. Notice how the lengths of the sides look about the same and the size of the angles look about the same. It's very neat. Compare it to this 5-sided object. This one is ragged. Look at that. That's just annoying. I don't want to deal with that one. Here's a 7-sided regular polygon, and here's a 7-sided freak child. They're just neater and cleaner. So good news is we focus on the regular polygons, and then you probably know that the number of sides gives the polygon a specific name. We know triangle, quadrilateral, maybe we know pentagons too, because there's that cool building in Washington. Hexes maybe, but after that the names get a little obscure. If you ever need to know, of course you can always Google what's a 12-sided polygon called, but the list is right here if you need them. Another word that we will use that's pretty obvious is the word diagonals. That's when you draw a line from one inside corner to another inside corner and connect it. Okay, so these are all examples of diagonals. You can go from any one point to the other points and draw a diagonal. Okay, let's talk about the different kinds of triangles that there are, because triangles, you know we love them, and we're going to talk about them a lot. Well, the neatest, tidiest kind of triangle, in my opinion, is the right triangle. Right? And in this one angle equals 90 degrees. That's what that little mark means, right? It means that it's the right angle. Now, we also have these weird suckers that look like they're tipping over. These are called obtuse triangles. And in these, one angle is greater than 90 degrees, right? This big fatty down here is more. That's why this is tipped so much, right? If we drew in a right angle, it would be kind of like that, just to help you see it. These overhang, and when we draw our heights on these, they weirdly hang out here. When we measure the base is only this part. Sometimes students think, well, maybe this is part of the base too. No. That's just weird overflow, this part here. This part would be the height of the triangle, and then this is just weird overflow. We don't need it. On these, the height of the triangle is equal to that side. I'm reminding you of this because you know when we go to measure areas of triangles, the height is really important. And then we have our other old favorite. This is the acute triangle. And in this, all angles are less than 90 degrees. And to find the height on these, it falls inside, right? And just as a reminder of my spider test, send the spider up to the top of the triangle and tell her to drop you her first web line straight down. That's how you can always find the height. Another important thing when we're talking about angles, which is what we're doing here, we're talking about angles of the triangle, right? We always want to remember this. When you add up the inside angles of the triangle, it will always equal 180. We're going to use that several billion times in the upcoming year. It's super important, so make sure you have that in your notes. I would put all of this in your notes. I'll draw one big one in the end, just a second. We talked about angles. Now let's look at triangles in terms of the number of their sides, rather, not the number of sides. They all have 3. Pretend that is perfect. These marks, which are called tick marks or hash marks, as you'll recall, when we put them on, that means they're the same. This is called an equilateral triangle because all sides are the same length, right? As opposed to this next guy in which 2 sides are the same, but the third is not. His name is isosceles. Cute little name. And it means 2 sides are the same. And then this last one is hard to draw because you have to be so kind of randomy. This one, I'm going to use the tick marks to show differences this time. And I can do this to show that that one's different. When the tick marks have different numbers, that means they don't match. This is called scaling, and all sides are different, which is another way of saying no side's the same. So we can classify the triangles in terms of their sides as well as their angles, right? 2 different ways to classify. We're going to spend a lot more time dealing with these types of triangles than we are these. This comes up some, and it's going to come up in these examples we're going to do, but over the course of the year, we'll be talking about these boys a whole lot more. Ready? Ready for your first example? I'm excited. Example 1.1. Oh, look. With the lettered lessons out of the way, we now have we have actual numbers. All right. Find x and y. I'll write that down just so we know. I don't expect you to write that down in your homework. That's overkill. Here's a little triangle. Again, I like you to draw the pictures because it helps you notice things. For example, you'll notice that there's 2 hash marks there, but there's not one on the bottom. Oh, there's not one on the bottom. So what that tells us right away is that this is isosceles. Is that going to help us? I don't know, but that's something I notice as I'm drawing, and I tuck it into my brain and move on. 50 degrees, X degrees, Y degrees. As I write that down, I think about the fact that these three need to add up to 180. Now, when you only have one, it's really hard to figure out the other two. Well, it's impossible, but I just think about that. All right, now, unless I remind you of this really important fact, this problem's pretty much impossible. Remember that there's a special relationship between the length of a side and the opposite angle. Right? There's a special relationship between them. It doesn't help us figure out what they are, but it tells us that they're the same. Another side with the same length is going to have a corresponding angle. So if these two sides are the same, then their angles must also be the same. So that tells us that x must equal 50 degrees. So the fact that these two sides match tells us that these two angles match, and so we know that x equals 50. Now we can figure out y, because it has to be 180 minus this 50 minus this 50, right? Both of these angles are 50 now, and that means that y has to be equal to 80 degrees. And guess what? Yay! It is. Excuse me, I just have to yell something about a cat. Hey, Jane? Does someone hear the cat? I saw that. I'm sitting by the window and I could see it's raining outside, and I saw one of our cats come running toward the back door, but I want to make sure that they see it. Okay. I'll trust that the cat will make it. Example 1.2. Tells you where my priorities are, right? I love math, but I don't want my cat to suffer. Okay, find x and y. Now we have a new picture to draw. Remember that it is always worth taking the time to draw these pictures. Always. Okay, we have an x here. We have a y here. We have 40 degrees. This reminds me of the last problem, in that we have one number for the three angles. That doesn't help us. In order to do the 180 trick, we have to have two. This, what the heck is that? That looks weird. I don't know what it means. And this is over there. Now, let me just point out, lowercase letters usually indicate angles. Uppercase letters, no. That rule doesn't hold here, never mind. I'll tell you about that later. Because we're using all of these to represent angles, so that rule of thumb doesn't work. Never mind. Okay, how are we gonna find out anything? One trick in solving these problems is to go alphabetical. The other one is to look at the numbers and see if they can help you. This one is not an isosceles triangle, so this number in here isn't gonna help us the way that that number helped us before. What is going to help us is this 150, because look, 150 and x form a straight line. That means this has to total 180. So x must be 180 minus 150. X equals 30 degrees. They're supplements, right? Supplementary angles, because they add up to 180. Okay, great. Now we're good. And now we can do y equals 180 minus 40 minus 30, because we figured out that x equals 30. So those two equal 70, so y must equal 110 degrees, and it does. So there are the two answers. Yay! Notice that last time I just put a big box around everything, and this time I kind of pushed the calculations out. Either way, whatever makes sense to you. Okay, we're moving on now. Ready? Here comes a fun topic. Transversals. I always think of Count Dracula from Transylvania when I think of transversals, but these don't scare me to death as Dracula might. We have two parallel lines. We use this little notation to remind us, yeah, they're definitely parallel. Through them, we karate chop a line, okay? Sometimes people ask, why don't we ever do transversals with a perfectly straight line? I'll show you why in just a minute, but there's one over to the side. What happens over here is we get this cool pattern of angles. We get a larger angle and a smaller angle. And they repeat as a pattern all the way down through this diagram. Notice that these two have to be the same because they're vertical angles. And these two are the same because they're vertical angles. Now over here, we can play a little game. Well, no, we know that these are going to be the same, large and small. Then we can also look at these as supplements. That's another way of looking at it. This is a straight line. So if this is the larger one, this must be the smaller one, and vice versa. So we get this cool little pattern where we only have two sizes of angles and they repeat. Now I can get to why this is boring. Because in this one, they're all just 90-degree angles. Here I showed it with the, right? It's just 90 degrees all the way down. All of them are 90 degrees. So that's why we don't usually look at this, because it's really boring. It's not interesting with a straight line here. It's much more interesting when our line is crooked. I recommend you put this in your notes in the cover of your book. It's super easy to remember, but it's very important to remember. So with that in mind, I'm going to flip so we can do our next exemple. We're getting close to the end. Example 1.4. Find A, B, and C. We have two lines that go like this. Now John goes really hard this time and he labels them M and N. I'm going to put that on my picture because you never know, but typically we don't need to know the names of the lines. Here's my karate chop. C, B, A, and, whoops, 60 degrees. That's a 6. Now, we know that the pattern is larger, smaller, smaller, larger, right? It always repeats. There's no mystery to that picture. I'm just going to draw it again right here. We can just look at it and go, okay, well, that's definitely the larger and that's definitely the smaller. Now I know they just repeat, alternating all the way down, right? So I can recreate this diagram really easily. Now all I have to do is figure out the single number we have. Is that the larger or the smaller? Well, I can tell by looking at it that it's the smaller. I also know that these two have to add up to 180, right? Because that's a straight line, so these two are supplements. So A has to be 120, right? Because these two have to add to 180. Now that I've got that, I know that my larger angle equals 120 and my smaller angle equals 60. And so all I have to do is look at my picture and say, is it a larger or a smaller? So let's do B next. B is definitely the larger, so it's a 120. And C is smaller, so that is a 60. Make sense? Let me make sure it's right. A and C are A is 120, B is 120, C is 60. Yay, all those are right. Okay? And our last topic builds off of transversals. It's got a fancy name. Proportional segments. We take our transversal diagram and we change it up just a wee bit. This time we're going to draw 3 lines. They don't have to be equally spaced. That's not required at all. John puts letters in and he puts these markers in to show again that they're parallel. And this time instead of one karate chop, we get two. And they're just random to each other. They're not, those look almost perfectly the same. They don't need to be. Now, John gives us numbers, not about the angles. We're switching our perspective now. Now we're talking about the lengths of the sides. And what we will find is that these segments are proportional to each other. Okay, and let me show you how that works. 2 over 3, these two segments, will be equal to 3 over 9 over 2. That's annoying that it's a fraction, but don't let it bother you. We can test my theory by saying if these are truly proportional, then we should be able to cross multiply and get the same number, right? They should be equal to each other. So let's cross multiply. 2 times 9 over 2, we're saying should be equal to 3 times 3. And look, these cancel, and then we get 9 equals 9. So my wild statement that I made, that these segments, right, we're not talking about the angles, we're talking about the length of the segments, they're proportional to each other because these guys share these parallel lines going through them. The parallel lines are what make the magic, okay? We don't have to get into a big philosophical description about why this is true. I just want you to see that 2 karate chops on a grid of 3 parallel lines will create proportional segments, and we can test it by cross multiplying. Now, the problems that use this lovely piece of information always look just the same way. We get the 3 parallel lines, and they're lettered P, M, and N again. Notice that we're not really using those names very much, so I'm not going to worry about them. We have one going like this and one going more like that. Again, remember, these don't have to be pretty. They can be totally wonky to each other. It's fine. This segment, John tells us, is 2 units. This one is 5 units. This one, he draws a little arrow like this and writes 8/3, and this one he calls X. He wants us to find X to solve for the missing segment. It's our last example for this lesson. Okay, so what we do is just like what we did before. We know that these segments are proportional to those segments, so we just create 2 fractions, and again, the easiest way to do this is just to grab the numbers as they're already arranged. So 2 over 5 equals 8 over 3 over X, okay? And notice that I made a distinction so that I can see that the 8/3 is clearly in the top of this main fraction, right? I make sure that one line is smaller and one line's bigger. All right, how do I solve? Cross multiply. 2x equals 5 times 8 over 3. I'm going to put this over a 1 just so it's easier to deal with. Then I want to divide by 2, but I stop myself and think that's going to create a mess over here. Better that I make this a fraction and multiply by the reciprocal. That I don't mind doing at all. That looks fine. But dividing by 2, oh no, too much. This is gone. X is by itself. Cancel there. And I get X equals 20 over 3. It's not real satisfying because what's 20 over 3? But we know, okay, 3 times 7 is 21, so this is just less than 7. That's the length of this one. Yay, it's the right answer. So in these, the math isn't hard, it's just knowing to set that up as a proportion. All right. We are done with lesson 1. Remember that we're now in the regular groove. I know I already told you to do this, but I'm just reminding you again. we're doing just our usual routine. We're doing the practice plus the odds for these problems, for this lesson, sorry. So no more random weird stuff, just practice plus problem set odds. Write that down to remind you. That's our homework from now until the end of time. Just kidding, I might change it for Thanksgiving. Okay, lesson 1. Thank you, goodbye.